Hello and welcome to our video on Hamiltonian Monte Carlo. Hamiltonian Monte Carlo, or HMC, is commonly used in Stan and NumPyro for statistical modelling. Over the past 8 weeks we've implemented HMC from scratch in Python, with a focus on it being a physics-based implementation where we keep track of physical constants which would usually be ignored. We use the implementation to estimate the parameters of a statistical model given some data, and our implementation is able to run on multiple GPUs. The justification for doing this is that sometimes these models are really large, which I'm sure other Summer of HPT participants will be able to tell you about. For example, models in genomics or disease modelling. HMC is commonly used to explore posterior probabilities. Let's say we have a model for something we can observe, and this model has parameters. Bayesian inference gives us a distribution for the parameters, gives us some observations that we make. This distribution is called the posterior. A simple example would be if we observe some coin flips with a biased coin. The bias could take a range of values between 0 and 1, and Bayes gives us a likelihood associated with these values. In our case, NumPyro will be performing this task, and we be using our own HMC kernel to sample from this posterior distribution.
So the problem we have is we want to sample or to get points that follow a given probability distribution function that depends on a parameter q. This parameter q is usually a multidimensional value. So the space spanned by this q is a multidimensional space. As a result, we should be really careful when sampling, where the product of the probability distribution function and the volume of this multidimensional space is non-zero. There are many ways to compute to sample from a given distribution, and one of these there exists a method called Markov chain Monte Carlo method. One of the most basic forms of this Markov chain Monte Carlo is the so-called Metropolis Hastings algorithm, and it basically works as follows. You start at initial position, you take at random, and from this position you propose a new point on your sample space, and based on this acceptance probability you take this point or you reject this point. But it's really important to keep in mind that as dimension increases, it's really hard to sample on the space where this product of the probability distribution function and the volume is important. So because of this, we move to Hamiltonian Monte Carlo. So now we talk about Hamiltonian Monte Carlo, or HMC, and for this, let's imagine we are given a particle, and this particle has positions, and we want this particle to move over a potential landscape, and this potential landscape depends on the particle positions. HMC actually expands the parameter space by adding an extra parameter which is called momentum, such that we now have a momentum and position for the particle. HMC, in addition, uses the information about the potential landscape in a really smart way, such that we drive or we guide the particle on the potential landscape such that we sample on those regions that are important. So that's the main difference between HMC and Markov chain Monte Carlo. So on the left hand side we see how Markov chain Monte Carlo behaves, or how it performs. We see that here we just move at random from one position to the other, and on the right hand side we actually compute trajectories. Instead of proposing points, we first compute, or we first explore the parameter space, and then on the final point of this trajectory, we compute the acceptance probability. By doing this, we are exploring much more the parameter space, and also by doing this, the HMC algorithm or method is more efficient.
We created our implementation using Google's JAX, which is NumPy accelerated on GPU. It's very well optimized and features just-in-time compilation as well as automatic calculation of gradients. We made use of the VMAP function to transform functions to allow efficient batching. MPI was used to run the program on multiple GPUs, where VMAP is then used to allow multiple chains to run in parallel. We achieved our initial goal of running HMC on multiple GPUs. This graph here shows the logarithm of the runtime versus the log of the number of particles, and you can see the speed up going from running on a CPU to running on 2 GPUs. Running simple models, our implementation was slightly faster than NumPyro, although this is not an apples-to-apples comparison, since NumPyro has more functionality.
We now move to the future work. We could first improve our implementation by changing how the step size and how many step size we need for the numerical method using Hamiltonian Monte Carlo, and also we need to test what the effects of temperature and masses of particles are on the performance of the algorithm. As well, we need to avoid communication between CPU and GPU for better performance. Finally, this is our main reference paper. We basically took all the information from this reference, and thank you very much for listening.